At trapezoids first. Trapezoids. Trapezoids are very easy to deal with as far as properties are concerned. A basic trapezoid really only has one technical part. It has one set of parallel sides. A trapezoid has one set of opposite sides parallel.
Are you always wrong with that?
You draw a bunch of different ways. So a trapezoid is a basic, because we'll have what we'll call like a regular boring trapezoid, and then we'll have the more specific isosceles trapezoid here in a second. So when you see a trapezoid, you know that you're going to have one set of opposite sides that'll be parallel. It does not automatically mean anything else but that. So what I want you guys to think of, though, is remember when we did back in good old chapter 3, parallel lines cut by transversals. I know, a long time. When you had parallel lines cut by transversals, you had all those different angle pair relationships. So if you had two parallel lines cut by a transversal, you had, alternate interior and so on. But if you look at it, and you're only looking at the angles on the inside, if these two parts are parallel and that's the side edge, what do I know about those two interior angles? They add 180. So the angles that are between the parallel sides, whether they're on either side, the angles between the parallel sides, these two and these two, they're not necessarily equal to each other or anything like that, but they'll always be supplementary to one another. So angles between parallel sides are supplementary. It's not technically a property that you see written out a lot of times, but I like to write it out for you because it's something that I know you're going to use, whether it's in a homework problem or a quiz or something like that. You see that part of it pretty regularly. Okay. Does that make sense, though?
Yes.
Thanks. Sorry, I just see shiny things with lights and trucks picking up school buses and things. It's kind of cool. I'm like a big kid. When you see like giant tow trucks and cranes and stuff like that, I just think it's awesome.
So you're a 7-year-old trip.
Yeah, exactly. It's just neat. It's just really cool. What's that?
You said 47, you didn't, yeah. So it must be pretty close.
I guess. Me too. Hi. What's up? Look, there's a big tow truck. It's picking up the bus that's broken.
Oh, wait.
Whoa. I know. Did you notice that throughout the day today, the big bus that's broken has a broken front door because the wind keeps blowing it open and shut?
Wow, Mr. Murphy, there's a lot of geometry happening out there.
Wow, Mr. Long.
Angles of elevation. It's not just geometry. There's physics. Ooh,
Oh,
fancy.
too bad we're in geometry working at trapezoid. He took your marker.
Whatever. Force equals mass times acceleration.
Oh, no.
Oh, yes.
Oh,
Yes.
yes.
Oh, no.
Oh, yes.
Get ready. Anyway, so it's not, back to this, it's not technically something you'll see written, but I do know, for instance, you're going to use it all the time, so you might as well write it down and see what that's like, okay? The more specific of the trapezoids is what we call the isosceles trapezoid. The isosceles trapezoid is the more specific of the two. We know this one because it shares a lot of the same properties of an isosceles triangle. For example, on an isosceles triangle, what do you know? Two sides are the same, which gives you what? Two angles that are the same. So with an isosceles trapezoid, you still have the opposite side, one set of opposite sides that are parallel. The non-parallel sides are congruent. Think of those as legs. Okay. The non-parallel sides will be congruent. And now think about isosceles triangle. Isosceles triangle has congruent legs, which point to the congruent base angles. Well, when you're dealing with a trapezoid, how many sets of base angles do you have? You have two. Wait, what?
Is that the same bus that was there yesterday?
Yes.
Oh, is that bus 21?
I don't know.
Oh, yeah, because they made an announcement, like, saying that, like, the bus 21 was gonna be, like, on the sidewalk today.
Oh, is that the bus number? I honestly don't remember. I really don't pay
Why, because
attention.
that's just been sitting
I
there.
understand that the bus 21 goes, but
I'm going to guess that it's broke down.
It is. It's broken.
By my professional eye, it could be one of two things. Out of gas
for the engine.
or the engine.
I say the engine.
I'm gonna go with
It
you.
might
I'm
be
gonna
batteries. It
err.
might have a dead battery because
True.
that's not necessarily engine.
Something in the front versus something in the middle or something at the rear. I'm gonna err towards the side of the front. So you've got two sets of congruent base angles. Now there's really no easy way to write down like which set are always going to be congruent to one another. But I think the easiest thing to do is remember that the angles that are on the same parallel part, if you will, parallel side. See how the two up towards the top, those two angles are congruent, the two on the bottom are congruent. If the angles share a side with the parallel part, those are the ones that are going to be congruent to one another. Okay. It's pretty easy just to think of it as in terms of base angles. So even if it is turned sideways or upside down or any of those things, so sometimes people freak out when they see them sideways. I know. These are still your congruent sides. Those are still your congruent base angles. Okay. You can always manipulate where things are drawn, and it's not a big deal. Okay. Questions on that at all? Oh, real quick. How many degrees are inside of a trapezoid? 360? Good. Because there's how many angles? 4. Oh, I almost forgot. One last property of an isosceles. The diagonals of an isosceles trapezoid, those are congruent. Okay. The diagonals of an isosceles trapezoid are congruent. It does not say if it bisects any angles. It does not say that they bisect each other or anything like that. All it's saying is that the two diagonals are going to be congruent. One of the reasons, the isosceles trapezoid, one of the reasons why we do that, or we show you this one, is because sometimes you can throw in a law of science problem to figure out the diagonal or to figure out a side length if you know base angles and things like that. There's a lot of stuff you can do with this. Another question came up last hour, I believe. Can I go to a clean picture? Well, thank you. people asked about, can you have two angles that are the same in a trapezoid? Well, a trapezoid only needs to have one set of parallel sides. Does not have to be isosceles. And if one of these angles is right, this one would have to be right. That is completely possible. It happens. It actually happens quite often. You could get something like that, and you could work and go through the rest of it. You can't have two sets of right angles in a trapezoid, because if you did that, then all of a sudden you wind up with rectangles and parallelograms, and that's not what we're looking for. Right? Does that make sense? You can have two right angles, as long as they're on the one transversal. Let me ask you this. What was this called? Don't say triangle. What was that part called? The what? The segment? What is it? The mid what? Mid segment. Good. We actually worked with mid segment a long time ago. A mid segment, and it's not so much for triangle stuff today, but what we're going to do is look at a mid segment in terms of trapezoids. So what'll happen is, we'll move this guy out of the way. If I can just delete everything. Mid segment is the segment that connects the midpoints of the sides. So when you have a trapezoid, the mid segment connects the midpoints of the sides. In a trapezoid, if you're connecting the midpoints, of the sides, that means you have to be parallel to the other two bases, we'll call them. The mid segment is the mid segment will be parallel to the other two bases. And this next one might actually look familiar from what we did when we had more than two parallel lines cut by transversals, where what happens was, so the mid segment, bless you, equals half the sum of the bases. The mid segment will equal half the sum of the bases. Bye bye, bus. Bus, go bye bye. It's cool that machines can do that. It's really neat. I mean, seriously, the scale of these things that can pick stuff up and move is just, it's awesome. You do. I know how much you guys love fractions. So let me move this, come up with this on a clean one here. Instead of using fractions all the time by taking half of something, how can you undo a half? Multiply by what? 2. That's called multiplying by a reciprocal. So one of the things, oh, I didn't write this down yet. We're pointing to nothing. One of the things you can do with this mid segment there's a couple ways to write out this formula. That's one way, and it works really well if your bases are even, because you can take half of even numbers pretty quickly. But the other way is to get rid of the fraction by doing this. Double the mid-segment, and it will equal the sum of the bases. Now, what I'm going to show you here is a couple of different examples of how you can write this out multiple ways. There is obviously going to be more than one way to do most of these problems, depending upon the information that you're given. For example, let's see if I have this open still. Guys, I don't have that much more to go through here, okay? But for example, one of the things that you can do is obviously the 12 is going to be the mid-segment because it's connecting the midpoints of the trapezoid. The two bases are the 16 and 4x. So there winds up being three different ways that we could write this out. We can write it out with the fraction, we can write it out without the fraction, and then we can write it out using logic. I know that's going to ask a lot. So the mid-segment, in this case our mid-segment is 12. That has to equal half of 4x plus 16. That's one way to write this out. Now, by writing it out this way, that means I can take half of the two numbers in the parentheses. What's half of 4? What's half of 16? So by using the fractional part here, it's not so bad. You'd get 12 equals 2x plus 8. Two-step equation, subtract 8, we get a 4, and you're left with 2. Not too bad, right? If you did not want to use the fraction piece, you would write it out differently. If I take my mid-segment and double it, it has to equal the sum of the two bases. What's 2 times 12? What's 24 minus 16? 8. And what's 8 divided by 4? 2. You're going to get the exact same answer if you math correctly. If you don't math correctly, you're going to get different answers. The third way is using logic. Now, we used logic back in first semester when we talked about midpoints. If you had a 3, -4, and a midpoint at 2 and 5, and you had to find that missing endpoint, remember how we went from, we'd say from 3 to 2, do you go up or down? How many did you go down? 1, so what's 1 less than 2? 1, so the next one would have been at 1. From -4 to 5, do you go up or down? How many? What's 9 more than 5? 14. Remember how we did that counting midpoints? We can do the exact same thing with this mid-segment stuff if you have two numerical values for either this segment in the mid-segment or the two segments on the outside. You can figure that out. So watch what happens here. Yeah?
I was confused why one side of it is the length is like, you see it has 2 dashes.
Yeah. This is a regular old trapezoid. As long as it's connecting midpoints, it can do that. All trapezoids don't have to necessarily be isosceles. This property still holds true if it is isosceles. Okay. You can have a trapezoid with vertical on one side and slanted out like this on the other. As long as the two bases are parallel, it works. All right. So from 16 to 12, do you go up or down? How many? 4. So what's 4 less than 12? So that segment has to equal 8. So what's 8 divided by 4? Each one of those methods will work. Logic or algebra. Sometimes one's better than another just because it's quicker than the other. That's all. Now that logic portion won't work if all 3 of those segment pieces are all written out with variables, which we'll get to probably more than likely tomorrow. But for today, we're just going to do numerical stuff. Okay? Let's try another one like that.
Wait, how did you get from 60 to 12?
Wait, what's that?
How'd you get
From 16 to 12, do you go up or down? How many? What's 4 less than 12? Same deal. Think of this one, try this one doing the logic again. We have the bases, we have a numerical value for one base and we have the numerical value for a mid-segment. So let's just figure out what the other segments, what the other bases value is going to be and work from that. Make it easier on ourselves. So the one base is 17, the mid-segment is 20. So did you go up or down? How many? 3. So the difference between these two is 3, which means I have to add 3 more to it. It's going to equal, and now you're at a 2-step equation. All by just counting. Okay? Just by counting. This is a very, very easy way to do this. Add 5 and divide by 7. And there you go. If you did not want to do that, double your mid-segment equals the sum of your bases. 40 equals 7x plus 12. Subtract, and lo and behold, you get the same thing. Okay? It'll work either way. All I'm getting at is, if we think about it in terms of not using a formula if you can, it's just less math. Okay? Does that make sense? Well, we still have a little bit of time here. Let's talk real quick about a kite. We'll look at the properties of that then real fast. Kite's the other shape we're looking at today. Think of a kite as 2 isosceles triangles put together. Think of a kite as 2 isosceles triangles put together. Now this one's always weird to draw. You get 2 isosceles triangles put together. So you do have 2 sets of congruent sides, but they're 2 sets of non-opposite. So these would be 2 sets of adjacent congruent sides. And then go back, think about if sides are congruent in an isosceles triangle, the base angles have to be congruent, correct? So if you have 2 isosceles triangles put together, you'd have 2 different sets of congruent base angles put together. If I add 2 things together that are the same, they're going to give me 2 bigger angles that are also the same. So what happens inside of kites is the angles between the sets of congruent sides are always congruent because of the properties of isosceles triangles. So the angles in between those two sets of congruent sides are always congruent. The last two, work with the diagonals. The diagonals of kites are always perpendicular because the height of an isosceles triangle is always the perpendicular bisector of the base. Properties from back in chapter 5. So diagonals will be perpendicular. And the segment between the congruent angles are always bisected. So the diagonal between congruent angles is bisected. We don't know anything else about the other diagonal. We only know the one diagonal that's put between the congruent angles. That one segment is always bisected. And the reason is because when you have isosceles triangle, the height of it is the perpendicular bisector of the side, and you get side angle side and corresponding parts and all that mumbo jumbo. Okay? Quick thing to remind yourselves of is notice again you have right angles, which means you're going to see, I don't know, Pythagorean theorem, SOHCAHTOA, triples, tons of fun. Okay. The problems I picked out for tonight, though, really don't have that much in terms of, don't have much in terms of the kites. We'll probably do more of those tomorrow. It's a lot of quick, easy algebra stuff, to be honest with you. Let me pull this up for you. I posted it already. And we'll go through more of this stuff tomorrow. All right?